Hello, I'm Dr. Jacob Hudis, and welcome to this video titled Rotational Kinematics, where I'll solve lots of problems. This is video 3 in my rotational motion playlist. Please like and subscribe for AP and college physics content and lots of great problems. On this slide, I discuss the quantities used to represent rotational motion. If you're watching this, you likely already know the variables used to represent linear motion. The Greek letter theta is used to represent angular displacement, and x represents linear displacement. This symbol is the Greek letter omega. It looks like a W, but it's not a W. It's called omega. And omega represents angular velocity. Omega sub-zero, also known as omega naught, is the same thing as omega I, which is initial angular velocity. Omega or omega f is final angular velocity. The analogous linear quantities are v, which represents linear velocity. The Greek letter alpha represents angular acceleration. It is units of radians per second squared. And a represents linear acceleration. In both rotational and linear motion, t represents time. When you're dealing with a circle, you can convert linear to angular variables by simply multiplying or dividing by r. For example, displacement, which is sometimes represented by the letter s. This is a little confusing because I have displacement as x over here, but s represents the arc length of a circle. This is another symbol that represents displacement. S is equal to theta times r, and therefore theta is equal to s over r. So if I know the angle an object rotates through, I can find the linear distance the object traveled by multiplying it by r. Linear velocity is equal to angular velocity multiplied by r, and linear acceleration is equal to angular acceleration alpha multiplied by r. Here's an animation from the University of Colorado website PhET. This will help you better visualize some of the angular quantities. There's a ladybug at some radius from the center on a disk that can rotate. I'll begin by rotating the ladybug. An angular displacement of theta equals 90 degrees. It's about 90 degrees. So that's what the angular displacement is. Now I've added two bugs to the rotating disk. There's one at a small radius and one at a larger radius. I click this button, which will allow us to see the linear velocity. Let's start the animation. And as you can see, the bug at a farther radius has a bigger linear velocity. They both have the same angular velocity, but linear velocity is equal to omega times r. Let's pause this. So because r for this bug is larger, it has a larger linear velocity even though they both have the same angular velocity. And if there was angular acceleration, then the angular velocity as well as the linear velocities would both be increasing in time. Before we begin solving problems, which is the best way to learn rotational kinematics, I want to present to you the rotational kinematic equations for constant angular acceleration alpha. These are the four kinematic equations. As you can see, they're almost identical to the kinematic equations for linear motion. The only difference is that v is replaced with omega and a is replaced with alpha. The first equation is omega final equals omega initial plus alpha times delta t. Equation number 2 is theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. The third equation is the only equation that doesn't involve time. Omega final squared equals omega initial squared plus 2 alpha delta theta. The final equation is theta or delta theta is equal to omega average times t. These equations are derived with the condition that the acceleration is constant. If the acceleration changes at any point for any reason, these equations no longer hold. They only work for constant acceleration. Problem number 2. A wheel with a diameter of 70 centimeters speeds up uniformly from 130 revolutions per minute to 280 revolutions per minute over a time of 4 seconds. A. What is the angular acceleration of the wheel? B. After 2 seconds of accelerating, calculate the tangential and radial components of the acceleration for a point located on the edge of the wheel. I'll solve the problem on the next slide. To begin, let's write down the givens. The diameter of the wheel is 70 centimeters, so the radius is 0.35 meters. The initial angular velocity is 130 revolutions per minute. There's 2 pi radians in 1 revolution and 60 seconds in 1 minute. So this is equal to 13.6 radians per second. Omega final is 280 revolutions per minute or 29.3 radians per second. Part A asks us to calculate alpha, the angular acceleration. This is one of the kinematic equations. Omega final equals omega initial plus alpha t. We can rearrange this. Alpha is omega final minus omega initial over t. Plugging in the values for omega final and omega initial up here, we get alpha is 3.9 radians per second squared. Part B asks for the angular velocity and accelerations after 2 seconds. Omega final equals omega initial plus alpha t. Omega initial is 13.6 radians per second. Alpha, we just calculated, is 3.9 radians per second squared. And time is 2 seconds. So omega final after 2 seconds is 21.5 radians per second. What is the radial acceleration after 2 seconds? The radial acceleration, also known as centripetal acceleration, is equal to v squared over r. This is tangential velocity. I discussed this in the previous video on the playlist. You can always relate linear velocity to angular velocity by multiplying by r. So centripetal acceleration is equal to omega r squared over r, or omega squared times r, where r is the radius of the circle. Omega squared times r equals 1.6 times 10 to the 2 meters per second squared. Tangential acceleration is alpha times r, where alpha is angular acceleration. So the tangential acceleration is 3.9 times 0.35, or 1.4 meters per second squared. Problem number 3. A gear of radius r1 is driven by another circular gear of radius r2. When the two gears are in contact at their outer edge, what is the ratio of their angular velocities, omega 1 by omega 2? And here's the answer. The tangential velocity at the edge where the two gears meet has to be the same, otherwise they'd be slipping. So we know v1 has to equal to v2. We can relate the angular velocity to the linear velocity by multiplying by the radius. Omega 1 r1 is equal to v1, and omega 2 r2 is equal to v2. These are the tangential velocities, and omegas are the angular velocities. You can then rearrange this equation, producing omega 1 over omega 2 equals r2 over r1. This is the way gears work. When you shift gears on your bicycle and your car, you're changing to a gear with a different radius. Problem number 4. Imagine a building standing on the Earth's equator. Because of Earth's rotation, the top of the building moves faster eastward than the bottom of the same building. If an object is dropped from the top of the building at a height h, it lands slightly eastward of the point directly below. A. How far east does the object land? Express in terms of hg and the Earth's angular speed omega. B. If a bowling ball is dropped from the top of the 435-meter Steinway Tower, ignoring air resistance, how far east will it land due to Earth's rotation? Here's a tall skyscraper located directly at the Earth's equator. The bottom of the building is moving slower than the top of the building. This is because tangential velocity is equal to omega times r. The bottom of the building has a radius of the Earth. The top of the building has a radius of the Earth plus the height of the building. This picture's obviously not drawn to scale. v1 is the tangential velocity at the bottom of the building, which is omega times the radius of the Earth. v2 is the tangential velocity at the top of the building, which is omega times the radius of the Earth plus the height of the building. So if you drop an object from a high building and ignore air resistance, it doesn't fall straight downward. It also has a small horizontal displacement. Now let's solve the problem. Because the top of the building is moving quicker than the bottom of the building, there's a relative velocity between the top and the bottom, v2 minus v1. v2 is the velocity of the top of the building, v1 is the velocity of the bottom of the building, and that's equal to omega h. You can think of it as if the bottom of the building is at rest, and the top of the building has a velocity omega h towards the east. To find the time it takes for the object to fall, we use one of the kinematic equations for linear motion. Delta y equals 1/2 gt squared, g is the acceleration of gravity. You can rearrange this and get t equals the square root of 2h over g. This is how long the object is in the air, from the time it's dropped to the time it hits the ground. The horizontal displacement is equal to velocity times time. Velocity is equal to omega h. To compute the horizontal displacement, we'll replace h with the height of the building and omega with the angular velocity of Earth. For the Steinway Tower, this is 5.79 centimeters. If you drop something from the top of a 435-meter building, it won't just fall 435 meters down, it will also move a small horizontal distance of 5.79 centimeters. Problem 5 is the final problem. Determine the tangential velocity of a point on the Earth's surface located at latitudes 0 degrees, which is the equator, 60 degrees, and 90 degrees, which is the North Pole. This is a cross-section of the Earth. Here's a point at theta equals 0 degrees, that's the equator. Here's a point at theta equals 60 degrees, and here's a point at theta equals 90 degrees. All three of these points have the same angular velocity, but they have different linear velocities. Linear velocity is equal to angular velocity times radius, and these 3 points have a different radius. This is the radius of the Earth. This is smaller than the radius of the Earth, and at the top, the radius is 0. At the equator, theta equals 0, v equals omega r. The angular velocity of the Earth times the radius of the Earth equals 463 meters per second. At 60 degrees, the r is smaller. The r is equal to the radius of the Earth times sine of 60, and that gives a velocity of 401 meters per second. And at the equator, the velocity is 0 because the radius is 0. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.